So let's look at this system. Basically what we want to do is calculate out the pump horsepower. So I made a couple of assumptions here to make things a little bit easier for us, and that's specifically that we're going to assume that epsilon over d is 0.001. Now, the first thing that I need to do with this system is I want to draw my control volume, because that's very important for my energy equation. And so my control volume, as I go back here, is going to be around the entire system. So where we're coming into the system is going to be here at 0.1, and going out of the system here at 0.2. Why did I choose 0.1 and 0.2 for my input and my output to the system? Because I know a lot of what's going on at those points. I know what the pressure at those points are because they're exposed to atmosphere, so I'm in atmospheric pressure. I know the height of both of those because it's given to me in the problem. More importantly, I know the velocity of both of those points because they're surfaces of large tanks, so they're zero. So at this point, we need to make some assumptions to solve our problem, and I know I'm going to want to use the energy equation. So I have three assumptions that I have to make to use the energy equation. I need a steady flow. I look at that, there's nothing in the problem that says it's unsteady. I need an incompressible flow, and we're using water, so we know it's generally incompressible, so that we're fine with that. And we need a constant temperature flow. And there's nothing in the problem that's talking about heat bleeding around. So as I start here and look at things, I need to start picking it apart and solving it. So what am I going to do? I'm going to write my energy equation. I'm going to knock out the low-hanging fruit to find out what's left of my energy equation. I am going to rearrange my energy equation to solve for the head of the pump, because once I have the head of the pump, I know I can drop into my definition of the head of the pump, which will give me the amount of horsepower for the pump. And so to do that, I'm going to work through my normal steps. More than likely, it's going to be a turbulent flow, but I'll check that. I'll calculate out Reynolds. If it is a laminar flow, I can sit there and go, okay, this is what my friction factor is. If it's a turbulent flow, I'll go to the Moody chart. I will add up all the minor losses in the system, and I'll put that into my Darcy-Weisbach equation, and then we'll solve it. So just a couple things to note here as I look at this picture. Let's just identify the minor losses now, so I will be able to use that a little bit later. And so basically the easiest way to identify the minor losses is basically draw yourself a little streamline that just goes through the system, and then work your way down the streamline and point out every place where there's going to be a minor loss. I'll use red. So as I come in, there's going to be a minor loss right there at the sharp entrance, because that's changing things. I've got an open globe valve, sharp entrance. Hit that up and check that there. The pump will not cause a minor loss. Any losses that are within the pump will be taken care of in the head of the pump equation. Well, I have a 12-inch bend radius here, so I am turning things around. I am going to have to worry about that bend radius. I have a screwed elbow here. I have a half-open gate valve, and then I have a sharp exit. So those are going to be all the minor losses that I'm going to have to worry about later on in this problem. So let's start looking at things. And the first thing I'm going to do is I'm going to write out the energy equation. So on this example, a lot of this stuff I just have typed up so we don't have to look at my writing. And so basically, what do I have? Pressure over gamma plus v squared over 2g plus z, everything at n, which is going to be 0.1. And then I have the energy that's being carried out. Pressure over gamma plus v squared over 2g plus z, all that stuff coming out, plus h total. Now that's the term that represents our major and minor losses now, minus the head of the pump, plus the head of the turbine. Now, a couple things that we did note for knocking out the stuff. P1 is equal to P2 because they're both atmospheric pressure. V1 is equal to V2, surface of the large tank, so they're both zero, and there's no turbine in the system. So what I'm left with is on the left-hand side I have Z in. On the right-hand side I have Z out plus the H total plus the head of the pump. So if I rearrange that, the head of the pump is the height difference plus the total head loss. And I've already got Z1 and Z2, but I don't have the total head loss. I need to go and calculate out the Darcy friction factor for that. so I can solve the Darcy-Weisbach equation for that. So to solve the Darcy-Weisbach equation, I need to know a couple things. We're going to have to calculate out the velocity.